So welcome back, and in this video we're going to continue to look at the mechanisms of the benzene ring. So that's the electrophilic substitution reactions. Now you've come across adding bromine onto a molecule in several places. You looked at it with bromine water and an alkene. It was one of the first mechanisms you studied. And in that case we induce a dipole onto the bromine molecule, and the Br delta positive is strong enough to actually react. However, because the benzene ring is so stable, a delta positive isn't going to work. We need much stronger conditions, and we need a full positively charged ion. So like we used sulfuric acid as a catalyst in the last mechanism, in this mechanism we're going to be looking at iron bromides. Now this is what we call a halogen carrier. In other words, the iron bromide can pick up and carry a halogen. So the first thing we need to do is to form the iron bromide, or the iron 3 bromide. And I'm just going to react my iron and my bromine to make iron 3 bromides. Now, 2 of those, 3 there, and a 2 there. Quite often we miss this stage and we're just interested in the fact that my catalyst is iron 3 bromide. I can then react, and this is the important step, the iron 3 bromide with bromine, and notice this is bromine liquid, not bromine water or anything else, because it won't work. My iron bromide will pick up that halogen, will pick up one of them to become FeBr4 negative, and I'll have got a Br positive, and that's my electrophile. Once I've generated my electrophile, the mechanism is the same as the previous one. So I have my benzene ring, I have my Br positive, this is now my electrophile. I take the electrons from the ring, remember, to the Br positive. I then do not have a smiley face. I break the delocalization over one carbon, and it's the carbon where my Br group is and my hydrogen is, and I put a positive inside the horseshoe. The electrons from the carbon-hydrogen bond then go back into the ring, reforming the ring. So that's the next bit, and I get bromobenzene as my product, or one of the products, and I get that free hydrogen ion floating around. Obviously the hydrogen ion doesn't actually float around for very long, if at all, because it will quickly get attracted to the FeBr4 minus. We're going to regenerate our catalyst, FeBr3, and we're going to generate some hydrogen bromide. And it's this hydrogen bromide that we can test for. So we see these as steamy fumes. We could also bring up some ammonia gas towards the edge of my test tube, and I would see the typical white smoke of NH4Br, ammonium bromide. So we could also use silver nitrate to react with the hydrogen bromide by bubbling the gas through silver nitrate, and you would see the typical cream precipitate. However, my aryl halides, in other words bromobenzene, is completely unreactive towards sodium hydroxide or the silver nitrate, whereas the alkyl halides, in other words the halogen alkanes, would react both with sodium hydroxide to make an alcohol and with aqueous silver nitrate to again make an alcohol and also that cream precipitate again. So the benzene ring causes the halogen to be a lot less reactive than it would normally be. So whereas my halogen alkane would react with OH negative ions, my bromobenzene will not. So there are 2 special types of reactions with benzene rings. They are called the Friedel-Crafts reaction, after Mr. Friedel and Mr. Kraft. And there are 2 types of these: alkylation, ALK, and alkylation, which we're going to be looking at later. alkylation basically means adding an R group, a carbon chain, to my benzene ring. So again, we require a catalyst, that is anhydrous aluminium chloride. Now, anhydrous aluminium chloride is a covalently bonded molecule, AlCl3. Now, because it only forms 3 bonds with the chlorine and it has no lone pairs of electrons in its outer shell, it's described as electron deficient. It has a vacant orbital where you can put a pair of electrons. So, let's have a look at the reaction. So the AlCl3 will react with my halogenoalkane. And the halogenoalkane I've chosen this time is CH3Cl. So CH3Cl. And like iron bromide, aluminium chloride is a halogen carrier. So it will pick up this halogen and become AlCl4 negative. That will leave behind a CH3 positive group. And I'm going to put that positive on that carbon because that's where I've lost my chloro group from. And the mechanism becomes exactly the same as it did before. I'm going to take my benzene ring, this ring of delocalized electrons. I've got my CH3 positive group. The electrons come from the ring to the carbon. The carbon group is then added on to my ring. Remember not to draw a smiley face. Positive goes inside the horseshoe. I have a hydrogen joined on. I have my CH3 group joined on. The electrons from the bond between the carbon and the hydrogen go back to reform my ring. And I get as my product methyl benzene. CH3 group on top, and I've got that hydrogen ion loose. Well, obviously that hydrogen ion doesn't stay loose for long because it'll quickly react with the AlCl4- to reform the catalyst AlCl3 and to make hydrogen chloride gas. So the overall reaction would be my benzene ring reacting with my chloroalkane in the presence of my catalyst AlCl3 to make my methyl benzene and to make some hydrogen chloride gas. So obviously the organic product is methyl benzene. And I can add any number of carbons via this method. So if I wanted to add a C4H9 molecule, for example, I would start with C4H9Cl. These are called alkylations, ALKY, because you're adding an alkyl group. Hence they're called alkylation reactions. So the second type of Friedel-Crafts reaction is alkylation, ACYL, because we're adding a acyl group. The catalyst, again, is aluminium chloride, AlCl3, and the temperature, well, it works at room temperature, but it probably could do with a little bit of heating to about 30 degrees under reflux, just to make sure it all works out correctly. So we're going to use ethanoyl chloride as our reagent, adding on an ethanoyl group onto our benzene ring. Again, we need to form our electrophile. So again, we've got our aluminium chloride catalyst, our halogen carrier, and again, it's going to pick up a halogen. It's going to pick up the chloro group from our ethanyl chloride. And we get AlCl4-, and we get our electrophile. Now again, be very careful where you're putting that positive charge. That positive charge is on the carbon where we've lost the chloro group. And then the reaction is exactly the same as it was before. We have our benzene ring, same as we normally do. We've got our C with our double bond O and our positive on it, and then I've just got that methyl, that group on the end, because that's an ethanoyl group. Again, the electrons from the ring come to the carbon, which has the positive charge on it. We get our intermediates, breaking the delocalization, positive, pointing towards that C group where they lost the delocalization. Got hydrogen. We put the hydrogen's electrons, or the hydrogen-carbon bond electrons, back into the ring, reforming the ring, making our organic product. C double bond O bond CH3. So I've made a ketone here and got that hydrogen ion. Obviously that hydrogen ion doesn't stay there for very long because immediately it'll react with the AlCl4- to reform my catalyst AlCl3 and to make again HCl. So my overall reaction again, I get my benzene ring, my C6H6. I'm going to add my ethanyl chloride, which is CH3COCl. Again, it needs to be done in the presence of aluminium chloride catalyst. This isn't reactive enough on its own to work. I'm going to add that group on to my ring. Got that methyl ketone functional group now added on, and I get HCl. So the name of this organic product is quite a difficult one. They're annoying because it's no longer called benzene. This will be phenyl ethanone. So this is done under anhydrous conditions because if you added water, that would destroy the catalyst. It would hydrolyze the catalyst and would therefore stop it from working. So anhydrous aluminium chloride is a covalently bonded molecule, but if I hydrolyze it, if I add water to it, it would turn into the aluminium ion, a hydrated aluminium ion, and a hydrated chloride ions. And that would stop it working as a halogen carrier. Now, we can do that at the end of the reaction to prevent any further substitutions. So that just stops the reaction dead. So that finishes this section of the notes looking at the electrophilic substitution mechanisms of the benzene ring. In the next video, we're going to be looking at why some substitutes activate the ring, make it more reactive, while other substitutes deactivate the ring, making it less reactive. But until then, take care, stay safe, bye-bye.